Good evening, everyone. On the behalf of Department of Mathematics, Wilson College Autonomous Mumbai, I welcome you all in the today's session. Our today's guest is Dr. Mahesh Naik sir. He is an assistant professor at Department of Basic Science and Humanities, SVKM's NMIMS Mukesh Patel School of Technology, Management and Engineering, College, Mumbai. He will deal with the topic of matrices and determinants today. Over to you, sir.
Yes, thank you. So let's continue from where we had stopped yesterday. Is my screen visible and am I audible clearly?
Yes, sir. It is audible and all is okay.
Okay. So yesterday we saw different types of matrices. To name a few, involuntary matrix, nilpotent matrix, idempotent matrix, and we saw some problems based on the properties of these types of matrices, especially uh, some examples which were focusing on the properties related to the determinant and all of that. Okay, so let's start with a small example based on what we had seen yesterday, and then we'll proceed with determinants, the official definition of determinants. Okay, so let's take this multiple choice question, which is based on trace. We saw trace yesterday, and maybe some examples based on that. Okay, so the question is, A and B are two n-cross-n matrices, and which of the following options equals the trace of A square into B square?
Sir, C, third one.
Third, what's the reason?
Sir, AB whole square is A square B square. So,
But commutative always does not hold in the matrix multiplication.
Correct.
Square into V square is reduced to AB whole square whole raised to the power 2 when it is given that A and B are commutative.
Correct. So let's see. We saw this property. If we have three matrices, that's A, B, and C. Okay, this is equal to trace of. This goes in cyclic order. That's what we saw yesterday. So we have A, B, and C maybe. Okay, then we can accordingly replace this ABC with BCA, and also we can replace this with CAB. There is no other possibility to have this equality. It should go into this cyclic form. So if you start with some other form, just use that to proceed with the cyclic form and then get the option. So in this case, what we can only do is we can write A square as A into A, B square as B into B. Okay, and then if we apply this cyclic property, so we have C coming here or and so on, like BCA and so on. So if we use this property, so in such case, what will happen in this part of the bracket, A into A, B into B?
Sir, if we take first A into A, one matrix B and second B is C, then one B would goes to before twos of 2A, and then it will be B A V.
Okay. So see, look at this ABC. Okay, and then we have BCA starting with the second element. So if I use the same property here, and if I start with A, okay, so this will be equal to trace of A into B into B into A. Okay, so I'm starting with this and then accordingly attaching A. So that
Yes.
gives me
Yes, sir.
trace of A into B square into A, which is one of the option here. Rest of the things will require a lot of information like being commutative and so on to hold the equality. Okay, is that clear?
Yes, sir. This
Yes, sir.
cyclic order is very helpful in between the of something or computation of something. The cyclic order notation.
Exactly.
Mm.
Okay, so now let's proceed with the definition of determinants, and then we'll see the properties of determinants. So let's assume A to be a matrix A11, A12, A13 up to A1n, AN1, AN2, AN3, ANN. Okay, so as we all know, a matrix has to be a square matrix to talk about the determinant. And determinant is nothing but a scalar value associated with the square matrix. Okay, and we denote determinant with either the notation delta with the order, or we can use the vertical lines to denote the determinant of a matrix. Now to calculate the matrix, what we can do is we can calculate the cofactors of the matrix, which accordingly can be obtained by deleting the rows and columns. And we can define the determinant of the matrix as the summation of Aij, where capital Aij in this case is denoting the cofactor, and doing this for all i's. So I'm expanding over j and taking all i's into consideration. So we'll have to expand, we'll have to take a row into consideration, and along the row, we can accordingly calculate the cofactors by deleting that row and different columns, which are given by j. That's how we'll calculate the cofactor. Okay, and if we go along the columns, the determinant definition would be I going from 1 to n. We have Aij, in Aij, and this would be applicable for all j. Okay, so that is what we generally use. We look at the we look at this cofactors, and then we calculate the determinant. Okay. Otherwise, we also have a definition in terms of permutation. Okay, so we can also define the determinant of the matrix as the summation over sigma belonging to Sn, where Sn is the permutation group, which is given by the sign of sigma, and then the product of all ai sigma I, okay, where the product is going from I equal to 1 to. Okay, so this definition is based on the permutation. So in case if I am dealing with S2, okay, so we know that S2 will have only two permutations. So the first one would be the permutation where the elements map to itself, so the identity permutation. And in the second case, 1 would map to 2, 2 will map to 1. So these are the only possibilities. Okay, so I can call this as sigma 1 and this as sigma 2. And so since I'm talking about a permutation of order 2, actually I'm talking about a matrix of order 2. So let's say A11, A12, A21 and A22. And everybody must be knowing the determinant is simply given by A11 into A22 minus A21 into A12. Okay, but let's arrive to do this definition by using the definition of permutations. So determinant of A is a summation over the cycle. So let's take the first permutation, which is sigma 1. So if I talk about sigma 1, the expansion would be sine of sigma 1 followed by the product of A1 into sigma 1. So that's A1 and then the map of sigma 1 and then A2 and the map of sigma 2. Okay, then we have the second term. So plus, I'll go for sine of sigma 2, which is my second permutation. Then again, we have A1 sigma, the map of sigma 1. And what is this? Sorry. This is A1 sigma 1. And this will be A2 sigma 2. In the first case, I'm talking about sigma 1, sigma 1. And in the second case, I'm talking about sigma 2. Okay, so now what is sine of sigma 1, which is the first identity permutation? Okay, so the sine of sigma 1 is 1. One can calculate the sine of this by calculating the transpositions or the length of the cycle, and there are many ways to calculate the sine. So in this case, for the identity map, sine is plus 1. So we have plus 1 followed by A1, and for the first permutation, the map of sigma 1 is 1. So it's A1, 1 followed by A2, 2. For the second one, the second permutation, which is 1 going to 2 and 2 goes to 1. So we just have one transposition. Transposition is a cycle of order 2. Okay, and the number of transpositions help in deciding the sign. So in this case, it will be minus 1 raised to 1. So the sign of the second permutation is minus 1. Okay, and if I look at this notations, which is A1, sigma 2 of 1 is 2 and sigma 2 of 2 is 1. Okay, so that gives us the definition, which is A11 into A22 minus A12 into A21. Okay, so determinant could be defined by using permutation, and many of the properties can be accordingly linked with the definition which comes in this way. Okay, so likewise we can have expansion of a determinant of order 3. So in that case, we'll be dealing with S3. And how many permutations will be part of S3?
6.
Will be 6. So accordingly, all those permutations at sigma 1, sigma 2 up to sigma 6, we can accordingly have similar expansion, and we can arrive to the same formula that we ideally get when we use the normal expansion.
Sir,
Yes.
sir, here's the sign that determines, that means if the permutation is odd, that means we raise to the power minus 1 raised to the power odd number. And
Yes,
so
minus.
when permutation is even, so that means we need to do is that minus 1 raised to the power even numbers. Is something like that?
Yes, yes. Minus 1 raised to the number of transpositions. Transpositions are cycles of order 2. So if you can write the permutation in 2 transpositions, then it will be minus 1 raised to 2. If you can write down a permutation in 3 transpositions, then it will be minus 1 raised to 3.
So when it is an odd permutation, then sign will be negative, and for even sign will be positive.
Yes.
Okay, sir.
Okay, so let's quickly go through the properties of determinants. So firstly, we know that when 2 rows of the determinants are identical, so the determinant is 0. So the determinant is 0 if 2 rows or 2 columns are identical. Okay, moreover, even if at least one row is 0, it's still going to be 0. So even if one single row is 0, because we can choose to expand over that particular row, and then accordingly, since we have AI j, small aij multiplied with capital Aij. Small aij's will be all 0 because we choose that particular row, it will be 0. Okay, second, if we interchange two rows or columns, the value of the determinant will change by negative sign. Okay. Followed by this, if we talk about the triangular matrices.
Sir, I am not getting your voice.
Is not clear?
It's clear, sir.
Okay. If I talk about triangular matrices where with the upper triangular or lower triangular, in such case, the determinant of the matrix will be simply the product of all the diagonal elements. And so it will be A11, A22 up to ANN. Okay, this is a very helpful property when it comes to determinants. Let's look at a special matrix where we can calculate the determinant. So let's take this matrix of order 8 cross 8 and let the elements be A 0 0 0 0 0 0 B. Okay, similarly we have 0 A 0 0 0 0 B and 0 followed by okay, so likewise, I hope you all have understood how to, what exactly will be the steps beyond. So 3, 4, 5, 6, 7, and then we'll have B here. So along the principal diagonal, we have all A's, and in the opposite diagonal, we have all B's. I've missed an A here, maybe. Okay.
Along main diagonal, all element A, and cross diagonal, all are B.
All are B. Okay, so, and we want to find the value of this particular determinant. So let's say this is A, and we want to find the value of this particular determinant. So this is of order 8. So let's say delta 8. Now, if I start expanding delta 8 by using the first element, that is this, I will be deleting the row and the column. Okay, and so in this case, it will be A times minus 1 raised to 1 plus 1 because the element is first row, first column. And so this is how I will proceed. Okay, and then I will find the matrix of this particular order, which is 7. Again, when it comes to this submatrix of order 7, I will be expanding along A. Okay, and in that case, it will be A multiplied with the position is second row, second column. So minus 1 raised to 2 plus 2. Okay, and then what remains is this smaller matrix, which is of order 6. So let's say that is delta 6. So I chose the first element to calculate the determinant, okay, which gave me the next element as A. Okay, and I'm not going ahead after delta 6. Let's see what kind of relation we get at this step. Okay, now if I proceed like this with other elements, like the other elements are all 0, so it will be 0. Let's come to B now. So we'll be expanding with the help of B. So B and the sign, minus 1 will be raised to the index which is we are in which row? For first row and 8th column. So 1 plus 8. So I'm using this. Now we'll come to this element because this is what will be surviving in this case. So it will be B minus 1 raised to 1 plus 7. And again, a smaller matrix would be multiplied, which is delta 6.
So 2 plus 7.
2 plus 7, yes, my bad. So now this negative powers that we have of minus 1 and minus 2, the first part will have positive powers. So we have a square into delta 6. The second part will give me negative 1 and accordingly 7, 8, 9, 8 plus 1, 9. That's giving me
plus b square.
plus b square. So this was 2 and this is 7 and this was 8 and this is 1. Correct. So this gives me a square plus b square into delta 6. So that's delta 8. So we can see the link between this and we can recursively use this property to have a square plus b square. Okay, we can, since the structure is same, we can rewrite this as a square plus b square into delta 4. And we can proceed till the last one, which is delta 2, which will give us a square plus b square. So there'll be 2 more, right? So after this, there'll be one more step, a square plus b square into delta 2, and then a square plus b square. So that raised to 4, which is nothing but this particular matrix. Okay. So we can have numbers in place of this, but since the structure is decoded for this particular type of matrices, accordingly, we can utilize it to calculate determinants of similar matrices where A and B are replaced by numbers.
So what is the general form of this matrix for
This is
delta
8.
n?
So 8 and 4. So we can think about any even number. And so that will be equal to a square plus b square raised to n.
Sir, could you please explain from delta 8 is equal to a square plus b square whole of delta 6?
This, okay. So here we just took out a square and b square common, right? And then we have delta 6. So from order 8, we came down to, we expressed it in terms of order 6. Likewise, if I apply the same operations here for this 6 cross 6 matrix, which has the same structure like 8 cross 8. Is that clear? So this would be a square plus b square followed by a square plus b square into delta 4. And then again a square plus b square, a square plus b square, a square plus b square into delta 2. And then one more time.
Okay, sir, got it.
Let's look at an example, one more. Suppose I want to find the determinant of A, and we have this relation A cube is equal to 5A. A is of order 4 cross 4. Okay, and we want to find the determinant of A. So one of the properties which I didn't specify, if we multiply a matrix with K, and if we find the determinant of the same, it is equal to K power n into the determinant of A. So this K gets multiplied with, so when we multiply K with A, matrices we multiplied with all the rows, and then accordingly we'll have to pull it out from all the rows separately, and that gives us this. So we can use this property here, determinant of A cube equal to determinant of 5A, and determinant of A cube is same as determinant of A the whole cube, whereas determinant of 5A would be 5 raised to 4 into determinant of A. Determinant of A the whole cube equal to 5 raised to 4 determinant of A. That gives us determinant of A whole cube minus determinant of A equal to 5 power 4. And so we can have determinant of A common. Which implies the determinant will be either equal to 0 or, I'm sorry. So determinant will be either equal to be 0. One second, what I did from here. It would have taken 5 raised to 4 should have been taken on this side. So that's 5 power 4 into determinant of A equal to 0. So taking out determinant of A common, we'll have determinant of A square minus 5 raised to 4 equal to 0, which implies this is equal to 0, or determinant of A is equal to plus or minus square root of 55 raised to 4, which is nothing but plus or minus 25. So based on the property, if we multiply a scalar with the matrix, and if we go for the determinant of that in terms of A, it will be K raised to N into determinant of A. Okay.
Yes, sir.
We have seen this idempotent matrices yesterday. Okay, we saw that A square is equal to A if the matrix is idempotent. Okay, and we have seen that the determinant of such a matrix will always be either 0 or it will be equal to 1. Okay, so now in case if we have an example of checking if the matrix is idempotent or not, we can check it via the determinant. Like for example, if the matrix is 0, 1 and 1, 0, and if I want to check if this matrix is idempotent or not. Okay, so we can simply find the determinant, which will be equal to minus 1. And since the determinant is not equal to 0 or 1, we can accordingly conclude that the matrix is not idempotent.
Yes, sir.
Yes. So that's an indirect use of determinant that we can do here. Okay. Let's take an example again. Suppose we have a set of all the matrices of the form 1, minus 1 and 1, with all other elements equal to, the elements below the diagonal equal to 0, and A, B, C here in the upper triangle, such that A, B, and C, they come from the set of complex numbers. And also we want A square to be equal to A. Okay, so we have 4 options about S. So the set S will be singleton, infinite, empty, or we have insufficient data to talk about this. So, can we look at this?
Sir, empty.
Empty. Why?
Sir, as we can see that the matrix is upper triangular matrix,
Correct.
and so the determinant will be nothing but the product of diagonal element.
Yes.
So the product is -1. And
Perfect.
here it is given that a square is equal to a. That is a condition of idempotent matrix. And we know that the determinant of idempotent matrix is either 0 or 1, but we are getting -1.
Correct. So we won't be able to get both these things in the same matrix. And because of that, we won't be able to find a matrix which will hold both these things. And so the matrix will be, the set in this case will be an empty set. Okay. Okay. So let's proceed with the next type of matrix, which is again a special matrix that we can look at, a Van der Rohe matrix. Sorry, not matrix, determinant. So Van der Rohe determinant is actually useful, or it comes into picture when we deal with interpolating polynomials, and a lot of places like eigenvalues and so on in linear algebra. So in this case, we have this x1 to xn, the intermediate variables, and the determinant will be defined like this. It will have this structure. So the first column will be of ones, then we have x1 to xn, and the powers will go on increasing, and the last power would be n minus 1. So if the order is 3, it will be the square, and so on. And we have a good expansion formula to calculate the determinant, which is the product of all xj minus xi's, where I and j are between 1 and n. Okay, so this can be quickly utilized to find the determinant of any structure. Like if I talk about a matrix of order 3, so in this case, what will be the determinant of this matrix? Yes. Will be simply by using this definition that we have here, we can accordingly get the value of this matrix determinant.
Sir, it will be A2 minus A1.
So that's b minus a in this case.
And uh, C minus A and C minus B.
C minus b. Okay, so that's how we can calculate the determinants a bit quickly by knowing the nature of the determinants in such cases. Okay, so let's proceed further. Now let's talk about singular matrices. Okay, so after this we can proceed with rank and then the system of equations. Before that, we'll talk about singular matrices, which are matrices with determinant equal to 0. Okay, and we know that inverse, we'll talk about invertible matrices. Singular we have already seen. So invertible matrices. So the inverse of the matrix will exist only if the determinant is not equal to 0. So the matrix should be non-singular. Okay. So using this information, let's try to take up a question which has the requirement of this information. So let's say we have n cross n matrix, and each element is 1. Then let's look at the options. A must be singular, A must be non-singular, A may be singular, and A may not be singular.
Option
Option
A. 1. A must be singular. Determinant will be 0.
determinant will be 0
Zero.
always. Will it be 0 always?
Sir, I have checked for 2 by 2 order and 3 by 3 order. Maybe for more than 3 by 3. Yes, I don't know.
If the matrix of order 2 or 3 has all rows as equal to 1, by the property itself, you know that the determinant will be 0. So
Yes, sir.
moving ahead will always give you the determinant equal to 0. But we have missed out checking for n equal to 1. So a matrix
Yes,
of
sir.
1 cross 1 will be just 1. And so the determinant will be 1. So is it singular?
No, sir.
So the suitable options in this case are A
Maybe
may
one.
be singular, because we have seen for 2 onwards it is singular, and A may not be singular also, because for n equal to 1 it is not singular. Okay.
Yes, sir.
Let's proceed forward with the concept of invertible matrices. So a necessary condition for existence of inverse of a matrix is that it should be non-singular. So if let's take an example. If we have product of matrices and the inverse, suppose A and B are invertible, then in that case this is given by B inverse into A inverse, and this can be expanded to any number of product terms. A scalar multiplied with a matrix, and the inverse of that would be equal to 1 by k times the inverse of the matrix. So these are some simple properties of matrices that we can look at. Okay, so based on this information, let us think about if A and B are invertible matrices. Okay, and in such case, which of the following are true? So let's take some options. So let's say A inverse is invertible, B inverse is invertible, A plus B is invertible, and A inverse plus B inverse is invertible. Okay, so what we know is A and B are invertible matrices, and we want to check these options if they are invertible or not. So if A is invertible, which means A inverse will exist, right? And so A multiplied with A inverse will give us identity. Same is the case with B. So can we say the first option is correct?
Yes, sir.
Yes. If A inverse is inverse of A, then the inverse of A inverse will be A.
Hmm.
So likewise, we can say for both A inverse and B inverse. Now, what can we say about A plus B? Will it be invertible?
Maybe, maybe not.
Okay. So we can be sure only about A inverse and B inverse. So how do we decide that A and B is not invertible? So in this case, if I choose my matrix A to be I, and if I choose my matrix B to be minus I, right? So what will be A plus B?
Null matrix.
Null matrix. Is it invertible?
No.
No. But we know that A, which is identity, and B, which is negative of identity, are invertible. So A and B are invertible, but the sum is not invertible. So accordingly, this will not work. And the same set of examples can be used in this case also. Right?
Yes, sir.
For the similar example, if A is invertible, B is invertible, and at the same time, A plus B is also invertible, then which of the following will be invertible? So A is invertible, B is invertible. At the same time, A plus B is invertible. So can we say 3, A minus B is invertible? With the same choice of A and B that we took earlier, if A is
No,
identity, B is identity, it will give a null matrix, and choice of A and B is correct as identity because identity plus identity is also invertible, right? So 2I. So if I take the same, if I choose A equal to I and B equal to I can see that A minus B will be a null matrix which is not invertible. Same example would go for A square minus B square, right?
one will be correct.
One will be
Correct.
correct. So how do we show that?
If A is a matrix which is invertible, then its inverse matrix is also invertible. So if we are given that A plus B is invertible, so the inverse of A plus B, which is A inverse plus B inverse, is invertible.
Okay. So in a simple way, if we use this property that the product of invertible matrices will be invertible, so we can have A plus B which is invertible, multiplied with A inverse and multiplied with B inverse, which is also invertible. And if I pre-multiply with A inverse first, that would give me identity plus A inverse into B, followed by multiplication with B inverse, which will give me B inverse plus A inverse into identity, which is particularly A inverse plus B inverse, so it is invertible. Okay. Whereas in the second case, if I take A inverse to be 2i and B inverse to be maybe I, okay, then the assumptions still hold, but this will not be, or maybe minus I. This will again give us the null matrix and it will not be invertible. So the first option is true in this case. Okay, one last example. Let's pull on this, which is if A and B are invertible, or let's take A and B as any two matrices such that AB equals BA equal to a null matrix and A plus B is invertible. Then which of the following are invertible? A minus B, A square plus B square, A power 5 plus B power 5, and A cube minus B cube. So it is given that A plus B is invertible. And AB and BA is equal to 0.
A and B are individually invertible or not?
It's not given individually. So A and B are just matrices, but A plus B is invertible.
I think A square plus B square will be invertible.
A square plus B square will be invertible. So if I take A plus B the whole square, we know that this is invertible because A plus B is invertible.
Yes, sir.
Okay, and if I expand this, I will have A square plus B square plus AB plus BA. But it's given that AB plus BA is equal to 0. So what we remain with is A square plus B square, and this is already known to be invertible, so A square plus B square is invertible.
Yes, sir.
Okay, and if you look at all other terms, we can easily get them by expanding. Like if I go for A cube, if I go for A minus B the whole cube, I will always get A cube minus B cube, and then the other terms would eventually become 0 because of this thing. So A plus B power n will be A raised to n plus B raised to n. And if I go for A minus B raised to n, there are two possibilities. If n is even, it will be A raised to n plus B raised to n. If it is odd, it will be A raised to n minus B raised to n. Okay, so all of this will eventually be invertible. Okay. Let's look at a theorem, one small statement. So if A and B are any two non-null matrices such that okay, so A and B are given to be non-null matrices, and AB is given to be 0, a null matrix, and in such case, both A and B will happen to be singular matrices. Okay, so we know that AB is equal to 0 if we take the determinant of this equal to 0. It's going to be 0. So if I take determinant of A as not equal to 0, that will imply determinant of B is equal to 0. And if I take determinant of B not equal to 0, that will imply determinant of A is equal to 0. Okay. So invariably, we will get the other one to be equal to 0. So in case, if I take determinant of A as not equal to 0, suppose, and B, we can accordingly, so let's take determinant of A not equal to 0, and let's assume that B is not a singular matrix. Okay. So we know that AB is equal to 0. I'm assuming B is not a singular matrix. The determinant of A not being not equal to 0, which means A inverse will exist. So if I multiply this with A inverse A into B, will give me B equal to 0, which is a contradiction to the fact that B is a non-null matrix. Okay, which means A and B have to be singular matrices.
Yes.
This is a very strong statement that we can use in. Okay, let's proceed with rank of the matrix. So rank proves to be a very important characteristic of a matrix. And we can calculate the rank by using the concept of determinants, or we can proceed with row echelon form. Okay. So in case if I'm working with a rectangular matrix of order m cross n, so A11, A12 up to A1n, likewise AM1, AM2 up to AMN. And so suppose this is matrix A. Okay, so rank is a very important characteristics because it talks about how the data, how distinct the data is there in the matrix. So it helps in recognizing if there is any kind of duplicacy, redundancy, dependency in the data. So rank helps in understanding the overall element structure of the matrix, and it is denoted by the letter rho. So the rank of A would be written as rho of A. Okay, so in case if you're dealing with a matrix of order m cross n, it is always the minimum of m comma n. Okay, moreover, it can be lesser than that. So we have a threshold by default when we deal with m cross n matrices. So if there are 3 rows and 4 columns, so in such case, the rank will be at most 3. Okay. Moreover, we know that the rank of a null matrix is always equal to
0.
0. Okay, so for a null matrix, rank will be equal to 0. Now, from the matrix, what we can do is we can have sub-matrices. Okay, so accordingly, we can delete a row or a column and we can generate more matrices out of this matrix. Moreover, we can generate square matrices as a submatrix. And those square matrices can be used to determine the rank of the matrix. So in another form, we can define that rank is, it is the order of the largest square matrix having non-zero determinant. Okay, so in case out of this matrix, if I'm able to pull out, we will be always able to do that. So if I'm dealing with a 3x4 matrix, I can always locate a 3x3 matrix, which is the biggest square submatrix in the matrix. And if the determinant of that particular matrix comes out to be 0, okay, then we can be very sure that the rank is less than 3. So let's take a matrix A of order 3x3. So there are two possibilities. Either the determinant of this matrix is equal to 0 or the determinant of this matrix is not equal to 0. If it is equal to 0, if it is not equal to 0, then rank of A will be 3. Okay. Otherwise, the rank of this matrix will be lesser than 3, strictly lesser than 3. So which means it will be lesser than or equal to 2. So since I'm talking about a matrix of order 3, okay, so in such case, now I'm talking about all those submatrices of order 2. So how many possible submatrices can we go for of order 2 in a 3x3 matrix?
So 4.
4?
No, sir. There will be more, I guess.
Okay, we can use combinations and we can see how many possible submatrices of order 2 can be extracted from this. And if all the submatrices have, so I'm talking about 2x2 submatrices. And if all these 2x2 submatrices have non-zero determinant, okay, then we can conclude that the rank will be equal to 2. But in case if at least one submatrix has determinant equal to 0, okay, then in such case we can talk about the rank of the matrix being strictly less than 2. Now there are only two possibilities. That is, so when we come below 2, the rank will be either 1 or 0. 0 will happen only if A is a null matrix. And if A is not a null matrix, then accordingly the rank will be equal to 1. So via the determinant, we can talk about the rank of the matrix going by the concept of submatrices. Now this example I took of square matrix, but if we have a rectangular matrix, accordingly we can have several higher order submatrices, square matrices, square submatrices. Is that clear?
Yes, sir, clear.
Okay. Let's quickly look at some properties of the rank. So firstly, rank of any matrix and the rank of its transpose will always be equal. If the matrix A is non-singular, then the rank of the matrix will be equal to the order. So here in this case, I'm talking about the square matrix, so I can speak about the determinant. If I talk about the rank of the product of the matrices, it is always lesser than the rank of A and also the rank of B. Okay, and moreover, we can say that rank of AB is lesser than or equal to the minimum of the rank of A and rank of B. Also, rank of AB is equal to rank of A if B is non-singular. Okay, let's take maybe one or two examples of rank, and then we'll continue tomorrow again with the concept of rank.
Sir, if we having matrices having more orders like five orders, six orders, then uh, by finding rank by sub matrices, it will take lots of time.
So in that case, we'll go to row echelon form.
Okay, sir.
So
Sir, can I ask a question here
yes.
related? Sir, you have defined equivalently that highest rank of a matrix is the highest order of it, highest order of a non-vanishing minor. I mean, yes, and this result is quite useful in some case where the order is quite less 2 cross 2, 3 cross 3, or at least 4 cross 4. But it is a deeper connection with the theoretical aspect of this rank.
Yes, it is.
In computation, their row echelon form is quite helpful because they are easy to calculate. But just by seeing or inspection, the number of non-vanishing minor may be larger in for larger order. But can we say about if we just by seeing inspection that there exists some non-vanishing minor of a 5 cross 5 order matrix, so then can we conclude there's its
Yes,
rank?
that is the purpose. So if you get even a minor of whatever order, like order 3,
Yeah.
order 2, and then
Hmm.
if it is coming out to be 0, you can talk about the rank being lesser than that particular order.
Okay. Okay.
Yes. So that inspection is very much useful when we have higher order matrices. At some places even row echelon form will be difficult because the size of the matrix will be large,
Yes.
and doing elementary row operations will be difficult. So it's good to go for this.
Hmm.
Okay, we'll take 2-3 questions and we'll see the row echelon form tomorrow. Let's look at this one example on determinant, which I wanted to take before, which has appeared in some paper. So we have this matrix of order 2 cross 2, and the determinant of A plus I is given to be 1 plus determinant of A. And we have the following options. So we want to check if the determinant is 0 or equal to, if the matrix itself is equal to 0, trace is equal to 0, and so on. Since the matrix is of order 2 cross 2, it's you can take a general matrix, and we can have A plus I, which would be A plus 1, B, C, D plus 1. And if we talk about the left hand side determinant of A plus I, that would be simply A plus 1 into D plus 1 minus BC, which is AD plus A plus D plus 1 minus BC. Whereas on the right hand side, we have 1 plus determinant of A, which is 1 plus AD minus BC. So looking at this, can we conclude something? So both are given to be equal, which means this is given to be equal to this.
Determinant of A is AD minus BC.
Right. So these two things are given to be equal, right? So that equality gives us
The
A
A is
plus
equal to minus D, I think.
A is equal to,
Minus D.
what does that mean? Okay, A equal to minus D, yes. So A
Yes,
plus,
sir.
and what is this A plus D actually?
The
For
trace of matrix A,
the trace. So trace of A is equal to 0.
0.
Option 3 can be confirmed looking at this expression.
Sir, can I say
Yes.
about it is I think here it is not confirmed that the whether it is MCQ or MSQ, multiple option may be correct. Okay, and
Hmm.
for that purpose, we can see just by inspection. If we put A is equal to identity matrix, I mean A is I, then determinant of 2I is 4, and left side it is the only 3, I think. Sorry, 2. So 2 equal to 4 is not possible. That is why it should not, it should be determinant is equal to 0 and trace of A is equal to 0, I think.
But what you did is you took a very specific example.
Yes. For discarding option and
Right. So in this case, we should ideally go for a general thing. So when I talk about A equal to ABCD, this is something which is applicable to all the matrices of.
yes.
Okay. For discarding, you can take that example. Okay, one more example we'll take. And one second, just pick up the example. Okay, so in this case, V is a non-zero vector of dimension 3 cross 1. Okay, and we want to check, and A is given to be V into V transpose. So V is a non-zero vector of dimension 3 cross 1. We can take V as maybe A1, A2, A3. V transpose would be equal to A1, A2, A3. And so if you talk about V into V transpose, it will be a matrix of order
3 cross 3.
3 cross 3, which will be A1 square, A1, A2, A1, A3, A2, A1, A2 square, A2, A3, A3, A1, A3, A2, and A3 square. And it's given that V is a non-zero vector, which means at least one out of A1, A2, A3 will be non-zero. Okay, and we want to find the rank of this matrix A, which is this. So what will be the rank of this matrix?
Sir, option A will be discard, but B will be true as we can put one in the first row, anywhere one. So we will get one non-zero rows.
One of
So
the zeros will be
one is possible, and option B can maybe true and A is false.
B will be true and A is false. Okay, so we haven't seen this. I mean, I didn't explain about the row echelon form, and also we haven't spoken about the rank of the matrix using the rows. So one of the definition of rank is the number of independent rows in the matrix. Okay, and if a row is possibly obtained from another row, then that becomes a dependent row, and that will not be counted in the rank. So rank will be the number of independent rows. So in this case, we can say that if we multiply this first row with, if we divide with A1, okay, and if we multiply with A2, we will be able to generate R2, right? So
Yes,
R
sir.
is same as, what is it? A2 upon A1 into R1.
So
Similarly,
then we will be getting two linearly dependent rows.
exactly. So we'll have R2 and R3, which will be dependent on R1. So there will be only one row, which will be independent row. And that row, we can look at the row as non-zero row because it is given that V is non-zero. And since we have only one independent row, the rank will be 1, and other options can be discarded. Okay. So we'll look at the proper definition of row echelon form and more examples on rank tomorrow, and also we'll complete system of equations so that we can proceed with eigenvalues and eigenvectors. Okay, so we'll stop here for the day. If there are any queries, you all can ask me.
Thank you so much for such an engaging and wonderful session, Mahesh sir.
Thank you.
Participants, please note that next session will be on tomorrow, that is 27 November 2025 from 7 p.m. to 8 p.m. as per the schedule. Let us meet there. Goodbye.
Bye.
Okay, thank you. Goodbye, everyone.
Bye.